get a start. Just double checking, making sure it is recording. Okay, everything looks good. And we'll start today's lecture. Are there any questions about the homework assignment? Is anyone encountering any problems with the homework assignment? Yep.
So we're supposed to just get, after we use resolution, we need to get 0 or 0 as part of our, what we derive from that?
If you get to 0 or 0, you can stop.
Okay.
Because that means you have arrived at a contradiction, which means the theorem that you're trying to prove is indeed a theorem.
Okay.
So, but if you get to a point where you cannot have any new terms added because of resolution,
okay,
you should also stop, because that means you have hit a dead end, which means at that point the theorem that you want to prove is not actually a theorem.
Yeah. And I was able to get it for both, but
okay.
Yeah.
Yep.
Just to be clear, in it, the expression I got from the previous homework, that's true.
Yep. All right. All right. Question? You had a question? Yeah.
So it's open that we can submit it now?
I believe so. Yep. All right. So with that out of the way, what we'll do today is I just wrote a note on events, which talks about no. Events is not mine. This is Wikipedia, but this is mine. Okay, it's about counting, but it's not just counting. It is counting the number of possible outcomes, depending on what kind of problem you're trying to solve. So we'll take a look at this note here. But today's kind of demonstration is going to be working out all the chances of winning various Powerball prizes. Okay, we talked about that last time. So the question is, if I buy a single ticket, a single lottery ticket, what are my chances of winning 5 out of 5 lucky number but no Powerball? 4 out of 5 lucky numbers and Powerball, 4 out of 5 lucky number but no Powerball, and so on. So we want to figure out all those numbers. And there's a spreadsheet attached. It's empty at this point, okay? So the whole point of today's class is we'll populate the spreadsheet with the necessary calculation for all of those prizes. So let's go ahead and start with counting and see how far we can go with counting. And counting, once again, is not about counting just normal numbers, okay? It is about counting the possible outcomes and stuff like that. The first thing we want to do is to clarify the terms of what is a trial, what is an experiment, and what is an outcome in the context of an experiment. A trial is a single attempt to do something. Typically, it involves choosing something either by random, usually by random. Sometimes it's just a natural process, but there's a single observable thing that you can see after a single trial. So in this case, we have an example, like a lottery game, okay? So has anyone seen how lotto is done using an actual mechanical thing, with balls inside? So when you draw a ball out of the cage, that is a single trial, okay? When you draw the next ball out of the cage, that's a separate trial, it's a subsequent trial, and so on. When you flip a coin, okay, that's a single trial. But if you flip like your coin like 4 times in a row, it becomes a series of trials, which is called an experiment. Are we doing okay so far? Okay. So outcome is really just talking about what is possible as a result of the experiment. If you flip a coin 4 times, okay, what do you think are the possible outcomes in terms of head and tails?
50% for
You can have head, 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 tail, head, head, tail, head, and so on and so forth. Okay? And how many outcomes are we talking about when you flip a coin 4 times? 2 to the power 4, which is 16, right? So we have 16 possible outcomes in that case. Very good. What about lottery tickets? What kind of outcomes are we talking about when we are talking about exactly Powerball? Do you guys still remember the rules of playing Powerball? Okay, we'll find out. Okay, Powerball.
It has its own pool that it grabs from.
Say again?
It has its own ball pool that it grabs from, right?
Right, but the rule of the game is okay. So we'll go back to the page that we were at last time. So we'll go to California version and right here. Oh, actually, we can just click on how to play, because how to play, shows you, how it is done. So we say, pick 5 lucky numbers from 1 to 69. So in the game, when they want to find out what the actual 5 lucky numbers are, that's an experiment. Plus the Powerball number itself, that's another experiment. Well, combined it is one single experiment, but it has 2 parts. So are we doing okay so far with this or not? Okay. So the experiment, quote-unquote experiment, in the case of playing lottery or Powerball, is to draw 5 balls out of a basket that has 69 balls to begin with. They're all numbered from 1 to 69, and each trial is picking 1 ball out of the cage. Is that okay? So now the question is, how many ways can we do this? Not counting the Powerball, which is a separate thing.
69 times 68.
Right? Yep, exactly. So it's 69 times 68 times 67 times 66 times 65. Okay? So now the next question is, how do we come up with those numbers? So we want to talk about general counting first. Okay? So if I use T subscript I to represent the outcome set of a single trial I, where I is 0 oriented, so the first trial is T0. So in that case, where Ti does not influence Tj, where j is greater than I. In other words, one trial does not affect the other trials. When you want to look at, if you want an example of an experiment where one trial does not affect the other trials, flipping a coin is one of those. Okay, you flip a coin, assuming your coin is not damaged in the process of flipping. The second flip of the coin, the first flip does not affect the outcome of the second flip at all in any way. Is that okay? Is that making any sense? But in lottery it does, because in lottery you start off with 69 numbers to begin with, but after the first trial you only have 68 numbers left. After the second trial you only have 67 numbers left. So in that case it is no longer fulfilling this requirement. So assuming that your trials are independent, then the set of all the outcomes in terms of an experiment as an experiment itself with M trial is going to be the Cartesian product of T0 times T1 times T2 times all the way up to T subscript M minus 1. Is that making any sense? Okay. So when you want to look at the number, which is the cardinality of this entire big, Cartesian product, then you're really just looking at, the product of I going from 0 to M minus 1, and then you're looking at the cardinality of each T subscript I. So are there any questions about this part? The outcome space has a cardinality of, and this is just a product of all the cardinality of the individual trials. Yep.
What's the symbol?
Or the big pi symbol? It's kind of analogous to the sigma symbol, except this is not for summation. This is for the product of all of the terms. So it would be the same thing as the cardinality of T0 times the cardinality of T1 times all the way up to the cardinality of T subscript M minus 1. Is that okay? All right. So in a lot of cases, T subscript 0 and T subscript 1 and all the way up to T subscript M minus 1, they're all the same. in the case of flipping a coin, they're all the same because you only get head and tail, right? No matter how many times you flip the coin, each time you flip the coin, you only get head and tail. So in those cases, it is very easy to deal with because if we assume that the cardinality of t itself is n, then doing this experiment m times or having m trials would have a cardinality of n to the power of m elements in the outcome set of the experiment. So let me just summarize, okay? A single trial is doing one thing, okay? I'm choosing something, I'm flipping a coin, I'm drawing one single ball out of the cage. That's a single trial. A single trial has its own outcome, which is usually not very exciting. Flipping a coin has an outcome set of two elements, head or tail. Drawing a ball out of, in lottery, okay, at least the first one, you have a set of 1 to 69 as the numbers, and you're picking one of those numbers. Is that okay? All right. But we can also string or connect trials into experiments. An experiment is basically a series or sequence of trials. Then you have to look into the trials, and then the first thing you need to determine is, does one trial affect the next trial or the subsequent trials? If it has no bearing and they're not related in any way, then you can just use this particular method where the outcome of an experiment of m trials is really just the Cartesian product of all the outcomes of the individual trials. Are there any questions about why we are using Cartesian product here instead of union or something like that? It's because for each element of T0, it can pair with any element in T1. For any combination of T0 and T1, elements from T0 and T1, it can combine with anything in T2, and that's why it is a Cartesian product. Yep.
So for like flipping coins, your I guess your Cartesian number off of that would be 2. Okay. So and then the lottery would be like 69, and that would be.
Well, in lottery it's more complicated because in lottery you cannot use just that anymore because your.
Well, I mean at least for the first instance for T0, and then moving to the T1 would be 68.
Right.
Okay.
It'll be, if you just look at the cardinality, you can figure out, the cardinality of T0 is going to be 69, the cardinality of T1 is going to be 68, and so on. But when you want to look at the actual outcome, it's not as simple anymore. You cannot just have a cross product and say, oh, okay, now we have all the possible outcomes of that particular experiment.
It's affected by the previous experiments, or
Because it is affected by the previous one. In other words, you cannot have 69, the number, okay, 69 is not a good one. So you cannot have, like 1, 1, 1, 1, 1 as an outcome of an experiment when you're dealing with lottery. Because once the ball 1 is chosen in the first trial, it is removed without replacement. So your second trial can no longer have a result of 1 because it's gone. Does that make any sense? Is that okay so far? Yeah, go ahead.
So the one that you have in the box up there, that not T1, that's for when you're doing the coin flip, right? Or something similar?
This applies to any experiment where each trial is not affected by any other trials. So as long as each trial is independent to all of the other trials, you can use this approach.
Okay.
Yep.
What about like regression towards the mean?
What about what?
So like if you're flipping a coin like on average, like isn't there like regression towards the mean?
Yes, there is, but in terms of the outcome space, it is still figure out this way. Yep.
So Cartesian product would work for coin flips, but not for the lottery?
But not for lottery, that is correct. So for anything that you're picking something, but the second trial has one fewer thing to choose from because you used it already in the first trial, you cannot just, the outcome space cannot be figured out easily like that anymore. Are we doing okay so far with this? Now, it might be helpful to just kind of take a look at an example. So we'll take a look at a quick example here. So in this experiment, or in this particular example, we'll just say that each trial has head, tail as the possible outcomes. Okay, because we're dealing with coin flips, right? So if you have a series of 5 coin flips, well, 5 is a lot. Let's make it 3. Okay. This becomes the possible. This is the set of all outcomes in an experiment of 3 trials, and then each trial is a coin flip. Is that making any sense? So when you look at this set, it is going to be a set of head, 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 as a 3 tuple in this case, because every time you use Cartesian product, you end up with a tuple. So this is head, 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 tail, head, tail, head, head, tail, 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 head, head, and so on. There are 8 of them, right? Is that okay? Is that kind of helping to explain the terms? Yep.
Does the order matter? And what?
Okay, the question is the order of what? The order within which notation? The parentheses, yes. But within the curly braces, no.
Yeah, I guess like within the parentheses.
Within the parentheses, it is important. In other words, head, head, tail is considered different from head, tail, head. They consider different outcomes from this perspective. Okay, good question. Anything else? Okay. No other questions?
So we're looking at the sequence.
Yeah, so
and
at
the
this point,
frequency.
the outcome is order dependent.
It's the sequence and the frequency instead of just the frequency.
Correct. We're not just counting frequency. We're not just counting how many of these trials end up with head and how many end up with tails. We're actually looking at the individual cases. Is the head the first trial, the second trial, or the third trial? So the sequencing becomes important. We'll figure out a way to remove that dependency later on, but at this point it is counted as important. Yep.
So it's permutations.
Yes, we're dealing with permutation, so we'll get to that term permutation later. Okay, very good. So is this part okay? All right. All right. So if I want to do this with lottery, it is not so easy, because with lottery, the first set is easy. The first set is okay for the first trial. The outcome set is easy because it's just 1 all the way up to 69. Anyone can figure that out, right? But for the second trial, it's not easy to figure out. Okay, for the second trial, the outcome set depends on what is used or what is chosen in the first trial. So I cannot tell you what the second, what the outcome set of the second trial is going to be, because it depends on, did we use 1 already? Then it's 2 to 69, right? If we use 2 already in the first trial, then it becomes 1 and then 3 and then all the way up to 69. If we use 3 already, then it's 1, 2 and then 4 all the way up to 69 and so on. So I cannot, the outcome set of the second trial is no longer independent to the first trial. Okay, so we'll figure out a way to generate that particular outcome space, but for now we cannot. Okay, it's not easy to do, at least at this point. Is that okay? All right. Okay. So getting back to the notes here. So without replacement is just like when you're dealing with a lottery game. So when you take something out, when you have chosen something in one trial, you can no longer use that again in all the later trials. So in this case, if E0 in T is the actual outcome of trial 0, or the result of trial 0, then E0 as an element of T is no longer available for trial 1. Trial 1 therefore has an outcome set of T minus the set that consists of only E0. Is this part okay? Does everybody understand what this means? It is everything in T except for E0. Because E0 is now used in the first trial. So for the second trial, you can only choose from this particular set. Is that okay? Which has one fewer element. When you're only concerned about, so to make it more general, if I use E subscript I to represent the actual outcome of trial I, then it's easy to see that for trial I, the outcome set is going to be the original T, which is all the things that are provided to you at the beginning of the game, or at the beginning of the experiment, minus the, oh, I used the wrong symbol here, dang it. This is supposed to be a big cup, which is the union representation, but I chose to use a big V, which is the OR notation. So I'm gonna fix that first. Okay. This is what happens when I type something like really, really early in the morning, 4 a.m. Well, I woke up and go like, oh, okay, I got a way to explain this, so I'm gonna do this. And this one is module 305.
It's used in 2 lines. There's 2 different instances of that same mistake.
Yep. Yeah, this one and the line following it.
Yeah.
Yep, so we'll go to 0305. And we'll look for big V. Uh-oh. I can see the bottom of this. There we go. So we're looking for big V. And we'll replace those with big cup. Okay, those are the only 2. We publish. And now it should be fixed. There we go. Very good. Okay, so we are looking at the union of basically just all the elements from E0 all the way up to E subscript I minus 1. J, sorry. Damn. I knew something else is wrong because I is used as a limit already, so the moving index is actually J, so that is supposed to be E subscript J and not E subscript I. So let me fix that also. So big cup. There we go. One more time. All right. Better. That's much better. But the idea is just that, okay? The idea is every single time you perform a trial, you're taking one element out that can no longer be used in all the later trials. So as a result, the number of choices or the cardinality of what you can choose from for trial I is now n minus I. Trial 0 is the first trial where I equals to 0, so you have everything available. For the second trial, I becomes 1, so now you have 1 fewer element to choose from, and so on. Is that part okay? Okay, right? So concept-wise, it is not that difficult. So if you have an experiment of m trials where T itself has n elements to begin with, then the possible outcomes for an entire experiment of m trial is going to be this number. So once again, the big pi symbol means the product of whatever the subterm is. And it's kind of like the big sigma thing, where it's a summation, except in this case it's a product. So in this case, I'm using I as an index to go from 0 to m minus 1, because from 0 to m minus 1, there will be m individual terms. And then the term that I'm actually doing the product with is n minus I. So that means I'm multiplying m to n minus 1 to n minus 2 to n minus 3 and so on, all the way until we get to n minus, and then in parentheses, m minus 1. Is that okay? More or less? Okay, it might be helpful to use actual numbers. So we'll try to use actual numbers, and we'll use some smaller numbers so it's more visible. So let's say n equals to 5, okay, which means we begin with 5 items. And we'll make m equals to 2, which means we have 2 trials in an experiment, okay? So for this particular experiment, for the first trial we got 5 choices, okay? And then for the second one we got 4 choices, and that's it. Then we stop, because we only have 2 trials for this particular experiment, which means as a total possibility, there are 20 possible outcomes in this case. So let me say that one more time. If you begin with 5 items, and in each trial, you have to pick an item out of whatever is left, but without replacement, which means once you take an item out of one trial, you can no longer use that item ever again in the same experiment, then there are 20 ways to arrange your choices. Okay? How do we spell out those 20 choices? Okay, so let's say T in this case is originally A, B, C, D, E. Okay, so what do you think would be the outcome? So the outcome set for the experiment is now the 2 tuples. You have A pairing with B. Okay, I'm going to do it this way so it's easier to copy and paste. Okay, so okay, it didn't quite paste the new line. There we go. So now we have A, B, A, C, A, D, A, E. Is that making any sense? It cannot be AA because it's without replacement, so AA is not possible. So the next 4 is going to be about the same, except they all start with B. So BA, BC, BD, and BE. And now we can copy even more faster. So now here we have CB, CA, CB, CC, CE, and then we have DA, DB, DC, and DE, and then we only have to copy and paste just a little bit more for all the E's. So we got EA, EB, EC, and then ED. That is the entire set of all possible outcomes for the entire experiment. Is that okay? Okay. And there are exactly 20 elements in this particular set. There are 20 possible outcomes when you have an experiment with 2 trials and you have 5 items to begin with. Is that okay? So for lottery, okay, if you don't care about the Powerball portion and just deal with the lucky number, then you have 69 items to begin with, and each experiment has 5 trials. I'm not going to write, enumerate elements of that particular set here, because you're looking at 69, times 68 times 67 times 66 times 65, and that would be the number of elements in that set. It would take me a little bit a long time to do it, if I do it by hand. If you do it using a program, it's not too bad. So are we doing okay so far with these terms? Okay. All right. So this part here has to do with the derivation. So we start up with this number, which is, we're just concentrating on the cardinality in this case. We're not concentrating on the actual outcome. We're concentrating on the cardinality of the sets of the outcome set. So do we have any questions about where we are starting off with? I is once again the index of the experiment itself. So when we're dealing with experiment 0, that's the first experiment, we have all n choices available to us. When I is 1, we have 1 fewer. When I is 2, we have 2 fewer elements, and so on, until we get to m minus 1. And m controls the number of trials per experiment. Okay. So if this is okay, can I multiply this silly number to the entire thing without changing the value. What is that? That's just 1, right? Because it has the same number for the numerator as well as the denominator. I can always multiply something by 1 and not change the value. Making any sense? Okay. But in this case, when you look at the original term, which is this part here, and you look at this term here, do you see how they actually connect? Because the term inside the big pi is the same. They're all dealing with n minus 1. But when you look at the indexes, the first one goes from 0 to m minus 1. The second one goes from m to n minus 1. Okay, they seem to connect. So that's why I can combine this term with only the numerator of this one, so that it becomes just one single series. So we go from 0 to n minus 1 in this case, and then the subterm itself is still n minus 1. Is that okay? Yes? No? It's okay? All right. But in this case, I can convert the numerator to just, a pi of 1 to n. Oh, okay. A gentle reminder. Go. It actually buzzed my charge too. All right. So but can everybody see how I can combine these terms and change the first pi into this? Can we see the connection between these two?
How did you convert that?
Yep, that's the question. So we only look at the n terms, okay? So we're trying to figure out what is the first term here and what is the last term, because we know it's sequential. Yeah?
Is m the number of trials?
M is the number of trials per experiment, yes. And then n is the cardinality of t, which is the number of things you can choose from for your first experiment. Okay, so when you look at this term here, n when I equals to 0, n minus I is n. Right? Okay. When you're at the very end, when I equals to n minus 1, n minus, in parentheses, n minus 1, just goes back to 1. So the range of the subterm that we are making a product out of is really just between 1 and n. Is that okay? So I can rewrite this pi into this pi over here, where I goes from 1 to n, and then the term that we're making a big product out of is just I itself. Is that part okay? If you need a little bit of time to look at this, that's fine, but I do want to make sure that everybody feels comfortable how I change the index, and then also change the term that we are making a product out of without actually changing the value. Is that okay or not? Okay, let me zoom in just a few more times, so this way I can point and click a little bit more easily. All right, so when you look at this term, okay, n minus I, what is the value of n minus I when I is 0? N, right? Okay, so there, and that's why we have this n over here. When you look at n minus I, what is the value of n minus I when I equals to n minus 1? Then you have n minus n plus 1, right? So it's just 1. And that's why we have this 1 over here. So instead of using the term n minus 1 in the product, I'm just using I here, because I'm just multiplying 1 times 2 times 3 times 4 all the way up to n. That's what the original one is actually doing too, except in the original one, it is multiplying n to n minus 1 to n minus 2 all the way down to 1. With the other one, it goes up.
And then you're just flipping the starting and end point.
Yeah, exactly. Is that okay? So I'm doing the same trick with the denominator. With the denominator, it's a little bit more complex, in a way, but it's not too bad. Because in this one, when you focus on n minus I, what happens when I equals to m? Well, when I equals m, n minus I is just n minus m. Right? What happens when I equals to n minus 1? When I equals n minus 1, n minus I becomes n minus n plus 1, which is just 1. That 1 goes here, and then the n minus m goes here. And once again, I'm not using the term n minus I anymore in the product. I'm just using I here. But the range of the value is still the same. I'm still going from 1 to n minus m in the product. In other words, I'm still multiplying 1 times 2 times 3 times 4 all the way up to n minus m in this case. Are we doing okay so far with this? So we're dealing with factorial, don't you think? The factorial of 5 is 1 times 2 times 3 times 4 times 5. So we are really dealing with factorial. So in the numerator, we're dealing with n factorial because this is the end of that multiplication series. And then in the denominator, we are dealing with n minus m, the entire thing factorial. Is that okay? And that's why we ended up with this term here. N factorial divided by, in parentheses, n minus m, and then the whole thing factorial. So are we doing okay so far with this derivation? Is everybody feeling relatively comfortable with this derivation here? Okay, all right. So there's a special name for this. It is called permutation. There are two ways to express this particular term, n factorial divided by n minus m, the whole thing factorial. You can use a big P, uppercase P, with n as the superscript, m as the subscript. You can also spell this out as P and then use two parameters, where n is the first, m is the second. N, once again, is referring to the number of items that you can choose from in the first trial of the experiment, and then m is the number of trials in the experiment. There are two ways to degenerate this entire thing. The first way to degenerate the entire thing is to say, I only got one trial. Okay? When you only got one trial, that means m equals to 1. So what do you think this number will degenerate into when m is just 1? We just get n back. Does it make sense? Your original T, you have n items to choose from for your first trial, and we only want one single trial. How many possible outcomes can I get? Exactly n, because I only got one trial. Is that okay? The other way to degenerate this is to say, what if I have n trials? In other words, I have as many trials as there are elements in the set to begin with. What do you think that's going to degenerate into? In other words, I'm asking you, what is P n comma n? You plug that back into the equation. You have n factorial divided by n minus n, the whole thing factorial. N minus n is 0. 0 factorial is 1. So we have n factorial divided by 1, which is just n factorial. Does that make sense? Yep. So you have to kind of test the n cases and make sure that those are all making sense. So are we still doing okay so far with all this stuff? Yes? Okay, maybe. Okay, when you have questions, just go ahead and ask. So the next item, which is in section 5, talks about ordering, because sometimes ordering does not really matter, okay? Because everything that we have done up to this point has to do with permutations. And in permutations, ordering matters. 1, 2, 3, 4, 5 is not the same as 5, 4, 3, 2, 1. But there are cases where ordering is not important, such as in lotteries, okay? Lottery tickets, the order does not matter. So now the question becomes, okay, given that we have chosen, these 5 things to begin with, how many ways can we rearrange these things? Well, we answered that question earlier already. because we have 5 things, and we have an experiment that have 5 trials in this case. So n equals 5, m equals 5 as well. Then you have 5 factorial divided by 5 minus 5, the entire thing factorial, which means we have 5 factorial ways to do it. Okay? So what that means is, when you look at the number of combinations, and a combination means we're still choosing items, but the order is not important. So CNM, okay, in parentheses, is also represented as n over m, but without the division line. Okay, it's called n choose m. So that is basically P, or the permutation of choosing m items out of n items. But we also want to make sure that we are not double counting anything. So we have to divide the whole thing by m factorial, because for each combination, there are m factorial permutations. So when you look at the total number of permutations of choosing m out of n items, you know that m factorial things should really be collapsed into one single combination. So when you work on the math, it just boils down to the last item, which is n factorial divided by m factorial times n minus m factorial. Do we have any questions about this part? Yes? No? Maybe?
I'm lost.
Okay, so we'll go with the example that we have talked about already. Yeah, go ahead.
I was just a little confused what the n choose m means for that. Like,
Okay, so what we'll do is we'll look at this. Remember this one? We got 5 items to begin with, and we're only choosing 2 out of the 5 items, right? So in this case, we have 20 permutations where the order is important. Is that okay? How many combinations do we have? When you choose 2 items out of 5, and you say order is not important. Okay, let me ask you another question. And we'll use different things. So if I say, what are the permutations of xy? In other words, I give you 2 elements, and I say, okay, how many ways can I arrange xy in different ordering? There are only 2, right? 2 ways. This is the first. This is the second. Because it is 2 factorial. 2 factorial is 2. Is that okay? So now we look at this and go like, okay, there has got to be some duplicates here. In other words, when I only want to deal with combinations, but I'm given permutations, I know that there's a certain ratio to this whole thing. Yes? Go ahead.
So m is like the possible choices. M is the amount of times you do those possible choices.
That is correct. So in the terms that we have already introduced today, m is the number of trials in an experiment, and then n is the cardinality of the set for the first trials. That's the number of things that you're given with. Okay. But in this case, we can see how each one there's a pair. AB is paired with BA, so these 2 belong to the same combination. Okay, because the combination is a set. AB is a set as a set, and then AC has its own duplicate over here, which is CA. AD has its duplicate all the way down here as DA, and so on. In other words, if you want to look at just the number of combinations but not number of permutations, then we only get the following. We only get 10 of them. Okay, so combinations of choosing 2 out of 1 A, B, C, D, E is the following. So this is a set on its own. So it is a set of sets. So we got one AB as one set. We get BA as a set. Is that okay?
Combination.
It's not good because AB and BA are exactly the same thing. Remember, in a set notation, order is not important. Whether I list A, B, in that order or BA in that order, it's still the same set. So this is not okay. But AC is fine. It's a distinct, new set. AD is a distinct new set. AE is a distinct new set. And then we go to B first, right? But I don't want BA anymore. BA is already covered by AB as a set. So BC is a new one. BD is a new one. BE is also a new one. Then we move on to C. I cannot have CA anymore. I cannot have CB anymore because those sets are already listed here. CC doesn't make any sense because it is without replacement. So CD is the next one. And then we have CE. And then we move on to D. D doesn't have a whole lot of choice anymore because D, C, D, B, D, A, we cannot use those anymore. DD doesn't make any sense. So we only got DE left. This is the set of combinations of choosing two things out of A, B, C, D, E as a set. So if you count how many elements do we have in this, the bigger set, how many have we got? 4 plus 3 is 7, 7 plus 2 is 9, 9 plus 1 is 10, which is exactly 20 divided by 2, which is also 5 factorial divided by 3 factorial times 2 factorial. Is that okay? All right. Okay. So I think we have enough terminology to solve the problems that I was mentioning at the beginning of the class. So now we go to the chances of winning various Powerball prizes. We go to this spreadsheet. Okay. Okay. So when we go to this spreadsheet, we are going to name different columns differently. Okay. This is me, but in the office. Okay. So we want to say n out of 5 lucky numbers. Okay. That's column B. And then this column is going to indicate matching the Powerball number. Okay. And what we're going to list here, okay, this part is n. All right, so we'll deal with jackpot first. The jackpot means n is 5. I want to match 5 out of 5 lucky numbers. And we also want to match the Powerball number. The question is, how many tickets are like that? Well, we know there's only one, okay? But how do we calculate that one? One makes sense intuitively, but it has to match the equations that we're dealing with as well, okay? All right, so we first want to ask the question, how many ways can I choose 5 things out of 5 where ordering is not important? We plug in that number. We plug in the equation, which is combination. So we say this is combin, okay, the combination of 5 things, and we are choosing exactly 5 out of 5. A2, the cell A2 is 5. And it tells me there's exactly one thing. There's one way to do it. Does that make sense to you? It does? Okay. If I want to match the Powerball number, how many ways can I match the Powerball number? There's only one Powerball number, by the way. There's only one way to match it because there's only one Powerball number. So there's only one way to do it here. So when you look at the product of these two numbers, of this number times this number, that becomes the number of tickets out of all the unique tickets that can win the jackpot. Is that making any sense? All right. Okay, let's look into the case where we still want 5, n to be 5, and we can just copy this one. But this time I don't want to match the Powerball number. So how many ways can I not match the Powerball number? The Powerball is chosen from 26 numbers. 25, very good. Okay, so we got 25 here. And so the product is 25. In other words, if you want to win the jackpot, there's only one ticket out of all the unique tickets that can win you the jackpot. But if you want the second prize, which is having all the lucky numbers matching, but not the Powerball number matching, there are 25 tickets out of all the unique tickets that can win the second prize. Is that okay? All right. But it gets a little bit tricky when n equals to 4. In other words, this time I'm asking, I only want to match 4 out of the 5 lucky numbers. The other number is not matching. How many ways can I do this? How many ways can I match only 4 out of the 5 lucky numbers and have one number that is not matching any one of the lucky numbers?
68.
Yeah, it's a little bit tricky. Yep, go ahead.
Is there or is the Powerball number, is that the 5th number?
The Powerball number is entirely different, so don't take that into
Okay.
consideration here. So we're only dealing with the lucky numbers. There are 5 lucky numbers. We want to match 4 out of those.
Out of
and then
69 choices?
out of 69 choices, correct. So the way to work on this one is a little bit tricky because in your head, you have to separate the balls or the numbers into 2 piles now. You have one little pile of 5 lucky numbers, and then you have a much bigger pile of 64 unlucky numbers.
So 63 by 25.
Okay? So is that okay in your mind? Okay. So the first part is easy. Okay? The first part is I want to figure out how many ways can I match 4 out of 5. Okay? Let's come in. 5 choose 4. 5 choose 4. Okay? We have 5 items. Choose any 4 of those. And combine 5, 4 will compute that. But this is not the answer. Because the answer also relies on what about the other slot of the unlucky number. So now you have to say, how many unlucky numbers do we have? 69 minus 5, right? Because out of the 69 numbers, 5 are lucky numbers. The rest are quote unquote unlucky numbers. So you have 64 unlucky numbers from which you're only choosing one of them. Okay, let's stare at this equation for a moment and make sure that we do understand what it means. Yep.
You use multiplication.
I did use multiplication, which is correct.
So what is the 5 and 4 saying?
Hmm?
What is the 5 and 4 saying in the comments? 5 and 4?
You're choosing 4 out of the 5 lucky numbers, and then you're choosing 1 out of the 64 unlucky numbers.
Right.
That tells you how many ways you can have 4 out of 5 lucky numbers. Because you have to take into consideration, okay, remember you have 5 slots. 1, 2, 3, 4, 5. I want 4 of these to match the 5 lucky numbers. But the remaining one has to be unlucky. How many choices do we have for the unlucky number? Exactly 64 this time. Yep. Mm-hmm.
Shouldn't it be 69 minus 4?
69 minus 5 is 64. You have to.
Why are you subtracting 5 instead of 4?
Okay, so the way to look at this is to do, so graphically, you say there are 5 lucky numbers. 1, 2, 3, 4, 5. And these are your lucky numbers. And then on the other side, you have a whole lot more. 64 unlucky numbers. So in order to win this particular prize, I'm asking you, how many ways can I pick 4 out of these 5 things? Okay, pick 4 out of these, and then pick 1 out of these, 64 items.
Right, so you're taking 4 away from the pool. So shouldn't it be 69 minus 4 and then
Nope.
that?
No, because the
Because-
fifth one can't also be a lucky number.
Right, exactly.
Because what?
Because the second part can only choose from the unlucky numbers, cannot be a lucky number. These are the 5 lucky numbers.
Oh, I see.
So regardless of how many of the 5 lucky numbers you want to draw from, it still doesn't change the number of unlucky numbers. It's still 64. Okay, very good. And this time I do want to match the Powerball number because that's a higher price, higher value price. So when I multiply these things, okay, undo. I think I just deleted it instead. There we go. So we have 520 unique tickets, your lotto tickets, that will match 4 out of the 5 lucky numbers, and also matching the Powerball number itself. So now we have 4, and we'll keep this one, except this time I have 25 ways of not matching the Powerball number. So in this case, I have quite a few more, 8,000 unique tickets that can win the 4th prize. The jackpot being the first. And then we have 3 down here. So now, I think we get the general equation, don't we? So we say combine, okay, 5, choose whatever A6 is, times combine 64, choose whatever 5 minus this number turns out to be. Is that making any sense? Okay, so let's take a look at this equation because I'm making it more general now. Instead of plugging in the 1 and the 2 and so on, I'm just making it general. Okay, so we're trying to match A6 out of 5 numbers. Those are the lucky numbers. In this case, it is 3. So I want to know the number of ways to pick 3 out of these 5 balls. Okay? Then we have 2 slots left for the unlucky numbers. So the 2 slots for the unlucky numbers, I have to pick 2. 5 minus 3 is 2, right? So we are picking 2 out of the 64 numbers that are not the lucky numbers. Then you have to multiply the 2 because they're, because for each way of picking 3 out of 5 of the lucky numbers, there are 64 2 ways to choose the unlucky numbers. Is that okay? Okay, so we'll take a look at this number. You can see how much bigger it is now. So let's say we also want to match the Powerball number. And so now we get this many tickets. So the next one is really about the same, except we want to match, we do not want to match the Powerball number. There are 25 ways not to match the Powerball number. Is that okay? So when you look at this, I don't know where the cutoff is. So we'll work out all of these cases. So we got 2 and 2. And then we'll work it down to 1 and 1. Okay, 1 and 1. Okay. What about 0? Sure, why not? Don't you think this should work with 0 as well?
So all unlucky.
Yep, exactly. And we should be able to go backwards too. In other words, I should be able to use the same general equation, plug it back to here, and also here, and change this to 5, 5, 4, 4, and they should still work out.
You hit enter.
Huh? I did.
For the
For number 4.
line
Oh.
5.
Yeah.
It's a little off.
There we go. Thank you. So the general equation still works. In other words, if I say I'm going to choose 5 of the 5 lucky numbers, I'm choosing 0 out of the unlucky numbers. How many ways can I choose 0 of 64 unlucky numbers? 1 way. Okay? 64 choose 0 is 1. Now, there are two ways to look at this whole thing. Conceptually, there's only one way. It's like, I'm not choosing anything. There's only one way of not choosing anything. Give you another alternative. So let's say you have 5 fancy pens, okay? Then you ballpoint pens, and I say, don't bring any ballpoint pen today to class. And then look at your backpack, there's no ballpoint pen. So how many configurations do you think you can have of not having a single pen in your backpack? 1, because there's only one empty set, right? And that's why 64 choose 0 is 1. What about 5 choose 5? You have 5 pens, and I say, bring all 5 today. There's only one way to bring all 5 pens, right? And that's why there's only one way here too. So you got 1 and 1, and that's why we got row 2. There's only one ticket corresponding to matching 5 lucky numbers out of 5 lucky numbers. And then plus, there's only one way to match the Powerball number. You multiply those two, it becomes 1. But what I'm also interested at this point is, I think this really should cover every single ticket, unique ticket in lottery with Powerballs. To be more specific, if I add up these numbers, I should end up with the number of unique tickets that can be issued for lottery, Super Bowl version. Does that make any sense? Because it seems like I have accounted for everything. Everything from jackpot to all the non-winning tickets. Yep.
Isn't that impossible though, since you could buy as many?
That's correct, but that's why I kept saying unique tickets. Okay? So how do we calculate the number of unique tickets that is in theory? Okay? So the number of unique tickets, I'm going to put it here, number of unique lotto or Powerball tickets is what? Well, let's see. We are taking combin. There are 69 numbers, of which we choose 5. Right? Because every time you look at a Super Bowl lotto ticket, it has got 5 numbers out of the 69. But we also have 26 numbers to choose from for the Powerball number. Is that okay? And that ends up to be, well, a number that we are fairly familiar with because we looked at this number last time already. 292 million and something, which is the chances of winning the jackpot. Okay. So I go back here and I say, if I add up all of these tickets, the summation of all of these, I really should come up to exactly the same number. And let's see. They're exactly the same. I think that's pretty cool. It's a good checksum to make sure that the calculation and the logic is not flawed. It's not a proof, but it's a validation. Yep.
How does the second one count for the Powerball or the Powerball numbers?
Not winning the Powerball number. So these are the ones where you're not matching the Powerball number. There are 25 ways of not matching, but only one way to match. Okay. Yep. Go ahead.
Do you win anything when you don't match the Powerball?
You still win some money, if I remember correctly. So when you look at past winning numbers, there's a place where it shows you, okay, these numbers matches the one that we have, I hope. Well, these are all expressed in 1 in odd, which means if you want to convert the number that we already have in the spreadsheet into 1 in. Okay, so how do we convert it into 1 in? Okay, 1 in. How does it relate to this? Yep, it's just really this number divided by this number. They're just looking at the reciprocal. Okay. So if I, okay, let me fix this first because because this number, you know, has to have the absolute reference. Okay, before I can kind of pull it down like this. So the Lotto website doesn't really give you the exact number, because your chances of winning this particular prize, which I think is $1, is actually 1 in 38.32. 32, 39, 39, 68, and so on. That's your chances of winning the lowest price of Lotto. Because I think you get $1 back. So every about 39 tickets you buy, you have a chance of getting $1 back. That's a 1-to-40 ratio, which is not very good. Yep.
I'm interested in like the amount of people that, like, when they don't like match all 5 numbers, the amount of people that come and claim like the lower prices, like if they even like know about it.
Okay, so that's a really good question. So what we'll do is they keep a log of, you know, how many people won each prize for the past few games. So we can look at number frequency. I don't think past winning numbers. That's it. Okay. So when you go to past winning numbers, it tells you in a particular draw what the winning numbers are and also what is the power number. But if you click on that date, it will tell you how many people win each particular level of price and how much money they earn out of each level of price. So you can see that, you know, if you just match the Powerball, you get $3 back, not 1. So that's a little bit better. So now you have a win ratio of 1 to 13 or so. So your average loss is 1 to 13, which means every time if you spend $13, you might get $1 back. If you spend your $39, you might get $3 back. That's the ratio. Yep.
So they're selling more tickets than possible unique combinations?
Only sometimes. Only sometimes. So that's a very good question, because now we can look at the ratio of number of winning tickets here, and then we can go back and figure out how many, or at least we can project or extrapolate what is the total number of tickets sold in this particular case. Okay, so we look at the Powerball, which is, you know, just matching the Powerball and not any of the lucky numbers. In this case, it's 47,166, 146. Yep, go ahead.
This is just for California though, right?
This is just for California, and only for that particular date.
So for US it's a lot bigger.
Probably. So I'm going to copy this number and we'll paste it into the spreadsheet. So we are talking about exactly this one. You know, it doesn't match any of the lucky numbers, but it does match the Powerball number. So we are talking about, so we put a number here, okay, 47,146. So there are 7 million tickets, unique tickets, that will get this particular prize for any particular draw. But only this many people went in and claimed the prize. So we can extrapolate and look at the ratio. So we can now say, what is this number, which is the number of unique tickets, times this number, which is the actual number of winning tickets for that particular draw, divided by the number of unique tickets that can win that particular prize. So now we get the actual numbers of tickets sold, or it's projected. Okay, it's not an exact number. So we are projecting that about 1.8 million tickets were sold for that particular draw, which is not surprising.
And that would have to be the case because it has to maintain the same ratios throughout the whole thing, right?
Right, because we are assuming that the probability of the distribution is even, is very flat and even. So there's always that off chance that, you know, maybe it's skewed. But that's why I chose this number, because as you choose the smaller numbers, the chances of a skew is even higher, because these numbers are much smaller to begin with, so they're not as accurate as an estimate of how many tickets were actually sold, because we are really just looking at the ratio. And you can also see whether the ratio makes sense or not. So we can compare these two ratio, which is about, I call this about 3 to 1, okay? And then we go back to our spreadsheet and we compare, what are we comparing? We're comparing this versus this one, I think. Okay, let me double check. Okay, so we're comparing Powerball versus one of the lucky numbers plus the Powerball. Okay. So we are comparing just the Powerball, one lucky number plus the Powerball. So we are comparing these two. So we are looking at about a 2.5-ish, kind of ratio. And then the other one is about 2.52. If you look at these two numbers, it's about 2.5. So the ratios are kind of close. So that tells me that my estimate of they sold about 1.8 million tickets is about right. Plus or minus maybe 0.1 million. Yep.
That means 1 in every 22 people in California basically got one lottery ticket, even though most people probably got more.
Yep. Not a whole lot, because the jackpot was only $140 million. And most people understand, 1 in, 292 million chance. So they say, hey, it's not worth it because, the jackpot is only $292 million. I mean, the chances of winning the jackpot is 1 in about 300 million, but the jackpot money, the payback is only $140 million. So it doesn't seem to make sense to most people because, when the jackpot hits like 300 million, you will probably see a very sharp increase in terms of sales because a lot of people forget that they have to pay taxes. So when it hits 450 or 500 million or so, you'll see another sharp increase. Those would be the bunch of people who understood tax consequences. When it hits maybe a billion, okay, then you'll see another sharp increase. Those would be the people factoring in that there may be multiple winners of the jackpot. Is that making any sense? So if there are historical data. If you want to understand the psychology of how people decide whether to buy lottery tickets or not, you can look at the jackpots, of all the past ones. What is this? Oh, that's just a number. Unfortunately, it doesn't give you any overview of the data. Okay, what is this? 472, 471. Oh, that's just a serial number. Yeah, it doesn't give us any straight number to begin with, so you have to kind of click on different ones to figure out what is the jackpot. This is a really, really low jackpot, so you can probably anticipate, even lower participation. You can see right here, Powerball is about a half of what we saw earlier because the jackpot is really low. So somebody can really probably plot a diagram of jackpot in one axis and number of tickets sold in the other axis.
I think I saw a blog that was doing that.
Oh, okay.
Yeah, I think there's a couple blogs that have traced that out.
Yep.
It's pretty interesting.
Interesting because you start to understand the human psyche. It's like, how many people will still take that chance? It's like, well, the jackpot doesn't look very attractive. You know what? I'm going to buy a ticket anyway. Yep.
And I was looking into it when they had the $500 million jackpot.
Uh-huh.
And it was they hadn't seen, because it was the biggest jackpot they had ever released yet, so they were really looking at what the number's going to be like, and it turned out that it's almost looking like it's exponential.
Yep.
The amount of people turning out compared to the price of the ticket.
Yep. But then those people are all forgetting to factor in multiple winners.
Yeah.
Yep.
How did they set the jackpot?
I think it has to do with how much money they were able to make from past sales, and the minus administrative fees and whatnot. So for this particular draw, you can actually figure out how much money they made. Okay, because they sold, we can look at this number and then anticipate how many tickets were actually sold. So you look at the number of tickets actually sold times the cost of each ticket or the price of each ticket. That's how much money they're making. And then from these numbers, you know how much payoff they're making. So they're paying 66 times 194 plus 111 times 120 and so on. So you know how much money they're paying off. In other words, in this particular one, they're not really paying a whole lot. They're probably paying less than $10,000. And then plus administrative fee, whatever is left is pure profit. So that adds up to the jackpot of this one. So the next jackpot is going to be this number plus whatever money they made in this round. So you can probably validate that particular theory by looking at the next one. Okay, which one did we look at last time? It doesn't matter.
Look at the top one, so you can look at.
Well, we can look at the September 2nd one. So I'm going to open up 2 tabs here. So from this, you can actually figure out the expense ratio too. How much administrative fees is actually deducted. So from this one, you can calculate the payoff, and also from this number, you can project how many tickets were actually sold, and then with this one, which is the following month, the following draw, you can see how the prize money went from 68 million to 83 million. So they probably made about $20 million of profit from the week before. So that just gets stacked up onto the second, minus the administrative fees and whatnot. So that's the way they do it. So when nobody won the jackpot for a long time, the jackpot gets higher and higher and higher, and then suddenly you have a whole bunch of people trying to buy tickets. So now you have multiple jackpot winners, and they go like again, and it has to take a long time to ramp up again. Yep.
You were able to calculate the number of, or to estimate the number of tickets sold using the 0.
Yeah, just using the ratio. So I'm using this number.
Not the total winning tickets.
You can do that too, but if you use this number, then you have to use the ratio of adding up all of these numbers, because the summation of all of these numbers would be the number of winning tickets among all the unique tickets. So that you can use that ratio as well. It's probably more accurate because now you have a larger number base to begin with. Yep. So next class, I think we can do some analysis of this whole business of running lotteries. So we can actually figure out the expense ratio of lottery, and then come up with a model of what is the cycle time, right? Because once it hits back to 0, it will take a long time to ramp up again because nobody's gonna buy when the jackpot is like $1 million.